we go. Okay, so doing just a tad bit of this lesson today. So a vector can be multiplied by a real number k called a scalar. This will change the magnitude, in other words, length of the vector. If k is negative, the vector will reverse to the opposite direction. The figure to the right shows various scalars of vector v. Okay, so here's our original vector v. If I graph 2v, it's just twice the length of v. That's it. If I graph 1/2 v, then it's half the length of vector v. The 2 and the 1/2, those numbers are called scalars. And then if I graph negative v, it has the same length or magnitude as v, but it's going in the exact opposite direction. So instead of starting at this point and ending here, it starts at this one and ends at the other one. Okay? We can add vectors geometrically or algebraically. We're going to focus on the algebraic method here, but this is graphically showing you what would happen. A geometric representation of the addition of two vectors, v and w, is shown to the right. The vectors are positioned so that the tip of v coincides with the tail of w. The sum of the vectors, called the resultant vector, extends from the tail of v to the tip of w. Okay, so geometrically, if I add v plus w, I graph v. Where v ends is where I pick up with w, and I sketch it at the proper angle and everything, get the correct magnitude. And then if I connect where this ends and this one started, that vector represents the sum of them. So in all cases, you're just forming a triangle. If I'm subtracting a vector, then that's the same as adding a negative vector. And a negative vector like spins it around 100 and 180, just 180, or 180. We'll stick with one of those, not both. All right, so if I graphed v minus w, I graph v, then where v ends, instead of w going, I'll just say up to the right, it's in the opposite direction going down to the left. Again, I connect where this one stops to where the first one started, and that is the difference vector there. Okay, but like I said, we're going to use algebra, which is 10 times easier than that. Okay, so scalar multiplication means you have a number, which is represented by k here, multiplying a vector. So if vector v is a1, b1, and I multiply it by k, then my new vector is ka1, b1. So it's kind of like distributing that number to everything in the vector. If I add vector v plus vector w, it is exactly what you might think. We take the first components, a1 and a2, and add them. And then we take the second components, b1 and b2, and add those. And then same with subtraction. If it's vector v minus vector w, I take the first component of v and subtract the first component of w. Go back to the second component, b1 minus b2, and that would be the difference vector algebraically. Okay, so super easy. Down here, let's use some actual numbers. If I had vector c, which is -4, 5, and I put a 2 in front of it, then it's 2 times vector -4, 5. And then it's like distributing. You just take both those components and multiply them by 2. So the new vector is -8, 10. And that's it. Okay, if I take vectors a and b and I want to add them, then I have -6, 2 plus 1, 7. And I take the first two components and add them. Take the second components and add them. So my sum is -6 plus 1, -5, 2 plus 7, 9. Okay, subtraction works the same way. Just be sure you put the correct one first. So I need vector c minus vector B. And you know that we tend to make more mistakes when we subtract, so be careful when you're subtracting. What is negative 4 minus 1? Negative 5. And what is 5 minus 7? Negative 2. Okay, this next one involves some subtraction and scalar multiplication. So I have A minus 3 times C. Now, we're either going to distribute a 3 and leave it a minus, or I think what I would prefer to do is make this plus a negative and then multiply by a negative 3 and change it to addition. So I would still have the negative 6, 2, but plus, now I'm going to distribute or multiply by the negative. So that becomes positive 12 and negative 15. And then I can add them, because I already dealt with the negative, so I don't need to subtract now. Negative 6 plus 12 is 6. 2 plus negative 15 is negative 13. Questions? Was I right? It's easy? Okay, you do the next two for me. I'm going to work them out up here, but I just won't talk through them. Okay, so you do 5 and 6. Using the same vectors on the previous page. Same thing.
Does the 1/2 only account for A?
Both of them. See how I multiplied 1/2 times 2? That's where I got the 1 from. So everything in there, both components get multiplied. Any other questions on those? Okay, so we're going to do 2 more examples and then we'll call it a day. Alright, so the next thing we're going to just touch on today is what a unit vector is. A vector with a magnitude or length of 1 is called a unit vector. Given any non-zero vector v, a unit vector u in the same direction of v can be written using the following rule. I'll give you the rule in just a second. Okay, so this is representing a vector u that has magnitude of 1. Kind of like unit circle has radius 1, unit vector has length or magnitude 1. Okay, let's picture if I had a vector that was length or magnitude 4. Okay, then the unit vector for this vector would be in the same direction, so it would kind of like fall right along with it, but have length of 1. Okay, so if this vector represents a length of 4, a length of 1 would be something like, I'm just going to estimate, might have gone too far, but let's just say that. Okay, so you have this vector, magnitude 4, and this little vector is magnitude 1, so that it is what fraction of the original one? 1/4. Okay, so if it was 10 for the magnitude, and I wanted a unit vector, it would be length 1, so it would be 1/10 of the length. Okay, so the formula that we use for a unit vector is 1 over the magnitude times the vector. So just like this magnitude of 4, the unit vector has length 1/4. Magnitude 10, a unit vector would be length 1/10. So that's why it's 1 over the magnitude. Okay, so let's do 7 and 8, and I'll show you how we find those unit vectors, and then we'll stop there. Okay, so find the unit vector u with the same direction as the given vector. Okay, so here's our vector, -5, 12. To find the unit vector, the first thing I'm going to find is that magnitude. Okay, so you did this yesterday. That's where we use the square root of a squared plus b squared, kind of like an x and a y squared when we found the radius of a polar coordinate. 25, 144, 169, which is a perfect square, so the magnitude is 13. Okay, so now we found 1 over 13. So the unit vector will be 1 over 13 times the vector times -5, 12. So that's a scalar multiplication. I'm going to take both components and multiply them by 1/13. So my unit vector will be -5/13, 12/13. And that would be the unit vector, same direction as that original vector, but 1/13 the length, so that the length of it is 1. Okay, the next one we're going to do actually is not 8. We're going to jump down to 9 and make that one our last one, because this one doesn't have a perfect square. All right, so here's the vector p. So I'm going to find the magnitude, aka the length, of vector p. So square root of that first component squared plus the second component squared. And that is 16 plus 1, square root 17 for the magnitude. Okay, so back up here to our rule. The unit vector will be 1 over square root of 17 times the vector. Unit vector is 1 over square root 17 times -4, -1. Okay, so I can do one of two things. I can go ahead and rationalize this number now and then multiply by it, or I can multiply and then rationalize. Which seems easier to you? And there's not a right or wrong answer. Multiply then rationalize? Okay. If you prefer to do the other, go ahead and rationalize that. What do I mean by rationalize? Multiply by square root 17 over square root 17. So that I get square root 17 over 17. Remember doing that? Okay, so I'm going to go ahead and multiply. -4 over square root of 17, -1 over square root of 17. But then if I rationalize these and multiply by square root 17 over square root 17, I get -4 square root 17 over 17, -1 square root 17 over 17. And that would be the unit vector.
Wait, so why did you even rationalize it if all you did was put square root 17 on the top?
I didn't rationalize at first. I was just saying if you want to, or when I said, do you know what I mean by rationalizing, I was showing you there.
Oh, so we didn't actually know.
I think it's probably easier to rationalize at first.
But
but I don't know. We did not.
Okay.
No, we did not.
Okay.
I rationalized after I multiplied. At some point you have to do it, so it's your call. Do it before you distribute or after you distribute. Question. We are done. I am not going to give you any homework. We'll finish doing a few more of these on Monday and talk about this little part here, and then cover what we were going to cover Monday, which is a tiny little lesson. And then we'll be done with this massive unit.
Now is where we need Wi-Fi. This is when we need Wi-Fi.
Because you have free time? Oh, my Lord. Can you find something productive to do, though?
I mean, it's Friday, so no.
I can check to see if I got accepted.
Did you just apply, though? Oh, y'all, why is my little record thing not on?
Oh, my.
Whoa.